Section 1 Introduction. In the introductory segment, we're delving into the impressive capabilities of large language models, or LLMs for short, which shine in tasks that require complex interactions and knowledge retrieval. For example, these models perform exceptionally well in open domain question answering and few-shot machine translation. The strength of these models lies in their exceptional ability to generate text. The transformer, a key system, was originally trained to predict a sequence of distinct tokens, but it's now being applied to handle natural signals like images or audio waveforms. This is achieved by transforming these signals into a stream of discrete units using a compression algorithm, which is then processed in a sequential manner, much like text. Within audio generation, the AudioPaLM framework has presented a unique, hierarchical approach. It uses two kinds of audio tokens. Higher-level, coarser tokens that are extracted from self-supervised embeddings are used to dictate the generation of lower-level codes from a neural codec. This approach is general and doesn't make too many assumptions about the audio signals being modeled. It has already been used successfully to generate speech and music. Specifically, in text-to-music or text-to-speech applications, a transformer model takes text tokens as inputs and produces audio tokens. Here, the text and audio vocabularies do not interfere with each other. Using this logic, these models can be converted into music captioning and speech recognition systems by simply swapping their inputs and outputs. Our thought is, if we can combine text and audio vocabularies into a single, multimodal vocabulary, we can train a single model to work in both directions. This leads us to the development of our new system, AudioPaLM, a multimodal generative model for speech and text. AudioPaLM's cornerstone is a shared vocabulary that can represent speech and text using a limited number of discrete tokens. This, in conjunction with a basic task description, allows us to train a single, decoder-only model on a variety of tasks that involve alternating speech and text. This setup includes speech recognition, text-to-speech synthesis, and speech-to-speech translation, bringing together tasks that are traditionally tackled by disparate models into one unified architecture. Another significant feature of AudioPaLM is that it's based on a large transformer model, allowing us to kickstart it with the weights from a pre-trained large language model. This gives our system the advantage of utilizing the linguistic knowledge and common-sense reasoning of models like PaLM or PaLM2. We've shown how this translation capability stems from the translation ability of the underlying text model. In this paper, our primary contributions include: 1. We're introducing a unified speech-text LLM that can handle and produce both speech and text, drawing on the existing capabilities of text-only pre-trained models like PaLM and PaLM2. 2. This unified approach lets us train AudioPaLM on a mix of tasks such as automatic speech recognition, ASR, automatic speech translation, AST, and speech-to-speech translation, S2ST. Our system achieves top-tier results on AST and S2ST benchmarks, and performs competitively on ASR benchmarks. 3. Our model uses AudioPaLM's audio prompting to perform S2ST with voice transfer for unseen speakers, outperforming existing methods in terms of speech quality and voice preservation. 4. AudioPaLM has shown the ability to handle scenarios it hasn't been trained for, specifically performing AST with speech input and target language combinations it hasn't seen before. The remainder of this paper is laid out as follows. We'll discuss related works, describe our method, provide details about the data we've used, present our experimental results, and discuss the influence of various design choices. The paper concludes with a summary of our findings. Section Summary. The AudioPaLM framework is a multimodal generative model of speech and text that uses a joint vocabulary to represent both speech and text with a limited number of discrete tokens. This allows for training a single decoder-only model on a mixture of tasks involving speech and text, unifying traditionally separate models into a single architecture and training run. The model achieves state-of-the-art results on automatic speech translation and speech-to-speech translation benchmarks, and exhibits zero-shot capabilities for AST with speech input, target language combinations not seen in training. Section 2 Related Work. Section 2 Related Studies 2.1 Fusion of different modes of information. The use of encoder-based models for learning features for various tasks is widespread. The purpose of combining the learning process of different modalities, such as audio and video, is to create a richer and more aligned set of features. This method is beneficial for tasks that require intermodality. Similar to the well-known BERT model, these encoders can be trained in two ways, using a masked language model objective for both multimodal and unimodal settings, or in a contrastive way. The latter approach results in separate encoders for each mode of information, each one improved by the other through the contrastive objective. A line of research on multimodal encoder-decoder models, also known as vision language models in vision-related literature, aims to combine text decoders with advancements in non-text encoder models. For instance, the Flamingo and Poly models from the vision domain, and the Whisper model from the audio domain are good examples of such combinations. These models combine an audio or vision encoder with a text decoder. The combination could be through adapter layers, as in the case of Flamingo and Whisper, or by using a separate encoder, as in the case of Poly. Both Poly and Flamingo use pre-trained components, which is beneficial because individual components can be frozen while the model is fine-tuned on multimodal data. However, Whisper does not use a pre-trained encoder or decoder and, therefore, does not freeze any components. The downside of using pre-trained components is that the output is constrained to text because the decoder used is text only. In contrast, we propose an approach that results in a model with a single decoder, which can handle sequences of audio and text tokens in any combination. This is similar to other approaches, except that we use only one decoder and all audio data is tokenized. Other models that use the encoder-decoder architecture accept continuous inputs and generate tokenized outputs for images. Section Summary. The section discusses various approaches to multimodal fusion, where encoder-based models are used to learn joint representations of audio and visual inputs. These models can be trained with a masked language model objective or in a contrastive manner. Multimodal encoder-decoder models have also been proposed, but they are constrained to only output text. The proposed approach is a decoder-only model that can model sequences of arbitrary audio and text tokens. Section 2.2 Generating Audio with Language Models. We've been exploring the process of generating audio using language models in recent times. The method under discussion revolves around using an autoregressive transformer network to generate speech. In this context, discrete tokens are represented as target tokens. These tokens can be extracted either from self-supervised speech or a neural codec. To give a little more clarity, when tokens are derived from self-supervised speech, we can model long-term patterns in audio sequences. However, this comes with a trade-off of offering limited reconstruction quality. On the other hand, tokens drawn from a neural codec provide excellent reconstruction quality, but the temporal structure is not as strong. To reconcile this trade-off, we've introduced a model named AudioPaLM. This model operates hierarchically. The first stage generates semantic tokens from a self-supervised system known as W2V BERT. The second stage uses these semantic tokens to produce the acoustic tokens of a soundstream neural codec. By jointly modeling both semantic and acoustic tokens, the system can learn the linguistic structure from various levels, ranging from syntactic to lexical and phonetic. All of this learning is done exclusively from speech-only corpora, without any text guidance. Additionally, the model can generate realistic speech from any speaker in varied acoustic conditions. We've also integrated AudioPaLM with a text encoder to form SPEAR-TTS, a model capable of text-to-speech synthesis. Leveraging pre-training and back translation, SPEAR-TTS only requires 15 minutes of labeled speech for training. What's intriguing is that the model learns to map between text and semantic tokens even with such limited data, suggesting the closeness of these representations. However, the model's architecture is specifically designed to take in text and produce audio, implying that the vocabularies of text and semantic tokens are disjoint and are modeled separately. Taking a different approach, SpeechLM uses a decoder-only audio generator, initially set with weights from a pre-trained text-based language model. While this approach facilitates some transfer of knowledge from text to speech modeling, the architecture isn't multimodal. The semantic tokens replace the text vocabulary instead of expanding it, and the model is fine-tuned on speech-only data. Finally, AudioPaLM aims to bridge these gaps. It combines semantic tokens and text into an expanded, multimodal set of tokens. These tokens are used interchangeably as inputs and outputs, allowing a text-only language model's pre-training to initialize a decoder-only model. This model can then be fine-tuned to perform a variety of tasks, like mapping between speech and text or even speech-to-speech conversions. Section Summary. The AudioPaLM model generates speech by using a hierarchical approach that produces semantic tokens from a self-supervised W2V BERT system, which are then used as conditioning to generate acoustic tokens of a soundstream neural codec. This allows the model to learn linguistic structure from speech-only corpora without any textual guidance, while generating realistic speech from arbitrary speakers and diverse acoustic conditions. The AudioPaLM model combines semantic tokens and text into an extended, multimodal set of tokens used interchangeably as inputs and outputs, allowing for text-only language model pre-training to be used to initialize a decoder-only model that can be fine-tuned on tasks that map freely between speech and text. Section 2.3 Speech-to-Speech Translation. The study of speech-to-speech translation, often abbreviated as S2ST, revolves around transforming oral language from one form to another. It aims to bridge communication gaps between individuals who communicate in different languages. The traditional methodology of automatic speech-to-speech translation comprises a sequence of three major components. Firstly, we have the automatic speech recognition, or ASR, which is responsible for converting spoken language into written text. Next, there's the text-to-text machine translation, simply called MT, which translates the recognized text from the source language to the target language. Finally, the translated text is transformed back into spoken language through text-to-speech synthesis, referred to as TTS. While the chain-based approach is effective, it mainly concentrates on the textual component, potentially neglecting important elements. These might include aspects related to the character of the speaker's voice, computational speed, compound errors, as well as precise translation of proper nouns and non-verbal communication cues that do not necessitate translation. However, certain direct speech-to-speech translation systems offer an alternative approach. They are trained from the beginning to the end to function on the audio spectrogram domain, thereby eliminating the need for text representation during inference. As a result, the audio that is synthesized can retain the acoustic information from the original speech, thereby maintaining the acoustic features, minimizing compound errors, and reducing computational demands. Furthermore, there are other layered S2ST systems that employ learned discrete speech representations as a midway representation. In these systems, the translation process operates within a learned discrete representation space. This facilitates the learning of alignments within this discrete domain and makes it easier to leverage text pre-training. Lastly, there are a variety of S2ST methods that enhance performance, computational efficiency, and data needs. They use weakly supervised data and pre-training of components to improve the accuracy of translation while requiring minimal parallel speech data. Section summary. The field of speech-to-speech translation, S2ST, aims to facilitate communication between individuals who speak different languages. Conventional S2ST systems use a cascade of three components, but may overlook important aspects such as paralinguistic features and nonverbal communication. Direct speech-to-speech translation systems operate on the audio spectrogram domain and can potentially reduce errors and computational requirements. Other S2ST approaches improve on performance, efficiency, and data requirements by leveraging weakly supervised data and component pre-training. Section 3 Method. In our methodology, we employ a transformer model that exclusively decodes, and it's designed to process sequences that are made up of both text and audio tokens. In the eyes of our model, these text and audio elements are simply sequences of arbitrary numbers, since they're tokenized before being fed into the model, and any results are detokenized before we return them to the user. We represent speech with specific tokens within a finite vocabulary, allowing us to create a multimodal vocabulary, which merges this audio vocabulary with a sentence piece vocabulary used for representing text. Consequently, our approach is almost identical to the traditional text-only setup using a decoder-only model. The only distinction is that in our scenario, some tokens stand for audio, while others represent text. We initiate our multimodal model using a pre-trained text-only checkpoint. A diagram illustrating the overall model is available in the paper. In this section, we will delve into the primary aspects of our model. Firstly, we will discuss how we tokenize text and audio inputs. Secondly, we'll describe the modifications we've made to existing pre-trained text decoders to also handle audio. And thirdly, we will explain how we transform the model output back into raw audio. The initial and final stages are the same as those used in previous studies, so we will only provide a high-level overview of these steps, and for more detailed information, we direct the reader to those earlier works. Lastly, we will go over how we fine-tune our model, which we call AudioPaLM, on a variety of combined speech and text tasks, including speech recognition and translation tasks that can involve converting either text to speech or speech to text. Section summary. The authors use a decoder-only transformer to model sequences of text and audio tokens, which are tokenized before being fed into the model. They build a multimodal vocabulary by representing speech with discrete tokens in a finite vocabulary, which is the union of the audio vocabulary and a sentence piece one used to represent text. The model is initialized using a pre-trained text-only checkpoint and is fine-tuned on a mixture of combined speech and text tasks including speech recognition and translation. Section 3.1 Audio Embeddings and Tokenization. In Section 3.1, we detail our methodology for creating audio embeddings and tokenization. We transform raw sound waveforms into tokens by borrowing methods from previous research. Our process involves two steps. First, we extract embeddings from an existing speech model, Then we discretize, or break down, these embeddings into a finite set of audio tokens. In our experiment, we used the W2V BERT model to extract the embeddings, and then we implemented a k-means clustering algorithm to perform the discretization. We've modified this approach slightly in two ways. Firstly, we employ a W2V BERT model that has been trained on data in multiple languages, not just English. Secondly, unlike previous work, we didn't normalize the embeddings before we executed the k-means clustering. Previous researchers found that normalization eliminated speaker identity data without hindering performance. However, our work in a multilingual environment revealed that normalization can actually lead to a decrease in performance. Our method results in tokens at a rate of 25 Hz, and we have a token vocabulary of 1024 unique tokens. In addition to W2V BERT, we also tested the Universal Speech Model, USM, specifically its 2 billion parameter variant, which is a higher performing encoder. We extracted embeddings from this model's middle layer and found that it, too, produced tokens at a rate of 25 Hz with a token vocabulary of 1024. Finally, we experimented with a second version of the USM model, referred to as USM v2. We enhanced this model with an additional automatic speech recognition loss, and then further fine-tuned it to improve its multilingual performance. Similar to USM v1, USM v2 takes raw audio as input and outputs a sequence of integers, with the sequence length being proportional to the audio length. Section summary. The process of converting raw waveforms into tokens involves extracting embeddings from a speech representation model and discretizing them into a limited set of audio tokens. The authors experiment with different approaches, including using a W2V BERT model trained on multilingual data, a universal speech model, USM, encoder, and a quantizer trained with an auxiliary loss. These methods produce tokens at a rate of 25 Hz and a token vocabulary of size 1024. Section 3.2 Modifying text-only decoders to model both text and audio. In the transformer decoder, an integral first layer following the pre-processing of input is the token embeddings matrix, denoted as E. This matrix serves as a translator between tokens represented as integers and their corresponding dense embeddings. Given a vocabulary comprised of T tokens and embeddings of size M, E is a T by M matrix where each row indicates the embedding for a particular token. Another similar embeddings matrix, denoted as E', is employed in the softmax layer at the end to compute the logits for all tokens at each position. This is an M by T matrix, and its product with the M dimensional output of the model results in a T dimensional vector of logits, one for each token. In the PaLM architecture, these matrices share variables such that one is the transpose of the other, meaning E' equals the transpose of E. The rest of the decoder architecture doesn't take into account the number of tokens modeled. We only need a minor adjustment to transform a text-only model into one that models both text and audio. This involves expanding the size of the embeddings matrix E to become a T plus A by M matrix, where A denotes the number of audio tokens. Consequently, the size of E', which equals the transpose of E, changes accordingly. To make use of pre-trained text models, we modify the existing model checkpoints by adding new rows to the embeddings matrix E. As for implementation specifics, the first T tokens range from 0 to T and represent the sentence piece text tokens, whereas the subsequent A tokens range from T to T plus A and represent audio tokens. While we can leverage the text embeddings from the pre-trained model, the newly introduced audio embeddings are initialized from scratch and need to be trained. We found that it's necessary to train all model parameters instead of merely retaining the previously established weights. We proceed with training using a mix of speech and text tasks, which will be discussed in detail in the following sections. Our findings show that incorporating audio tokens into a text pre-trained checkpoint significantly enhances performance on the evaluated speech and text tasks, as opposed to retraining from the beginning. For more in-depth information about the PaLM architecture, please refer to Section 2 of the original text. Section Summary. The PaLM architecture modifies the transformer decoder by expanding the size of the embeddings matrix E to include audio tokens, while keeping E prime equals E intercal. This allows for the use of pre-trained text models, with the new audio embeddings freshly initialized and trained. Training all model parameters is necessary, and adding audio tokens to a text pre-trained checkpoint improves performance on speech and text tasks. For more information, refer to Section 2 of the paper. Section 3.3 Decoding audio tokens to raw audio. In order to transform audio tokens into actual audio, we tested two distinct strategies. One is an autoregressive decoding approach, modeled after the AudioPaLM system, while the other is a non-autoregressive method, based on the recently introduced SoundStorm model. In both scenarios, we initially convert the audio tokens into SoundStream tokens, which are subsequently transformed into an audio waveform using a convolutional decoder. The audio generation within the AudioPaLM framework takes place in two phases. In the second phase, a transformer model that only consists of a decoder takes as input the audio tokens produced by AudioPaLM along with voice modulation. This results in SoundStream tokens that can be employed to generate speech in the desired voice, albeit at a relatively low bitrate. The third phase further enhances the SoundStream's residual vector quantizer levels, leading to an increase in bitrate and, subsequently, better audio quality. We employ the same hyperparameters and training process as previously utilized in the AudioPaLM framework. SoundStorm presents a different approach for non-autoregressive decoding, implementing an iterative method that operates simultaneously on all tokens. This leads to audio quality equivalent to AudioPaLM, but with more uniformity in voice and sound conditions, and at a speed that is approximately 100 times faster. We train both strategies using the multilingual Libre speech dataset, while a voice sample lasting 3 seconds serves as the voice conditioning. This voice sample is represented as both audio tokens and SoundStream tokens. By including a portion of the original input speech as the voice modulation, the model can maintain the original speaker's voice while translating their speech into a different language. In cases where the original audio is less than 3 seconds in length, it is looped until it meets the required duration. Section Summary. The section discusses two methods for synthesizing an audio waveform from audio tokens: autoregressive decoding and non-autoregressive decoding. Both methods use SoundStream tokens to generate the audio waveform with a convolutional decoder. The non-autoregressive decoding method proposed by SoundStorm is faster and produces audio with higher consistency in voice and acoustic conditions, while maintaining the original speaker's voice when translating their speech to a different language. Section: Types of tasks. We've implemented our technique to tackle challenges in the domains of speech recognition, speech synthesis, and speech-to-speech translation. We've worked exclusively with databases that encompass various combinations of the following components. 1. Audio. This is the original speech in the source language. 2. Transcript. This is a written representation of the speech content in the audio. 3. Translated audio. This is the verbal translation of the original speech. 4. Translated transcript. This is the written translation of the original speech. In this study, we've engaged with several tasks. 1. ASR. Automatic speech recognition. The objective here is to transcribe the speech from the audio into text. 2. AST. Automatic speech translation. The goal here is to translate the audio into a written transcript in a different language. 3. S2ST. Speech-to-speech translation. In this task, we aim to translate the speech from one language to another, maintaining the output in audio format. 4. TTS. Text-to-speech. The task here involves converting the written transcript back into audio. 5. MT. Machine translation. This task requires us to translate the written transcript into a different language, keeping the output in text format. Any given dataset may support multiple tasks if it includes more than 2 of the listed fields. Through our experimental investigations, we discovered that employing multiple tasks from the same dataset, such as ASR and AST, enhance the performance outcomes. Section Summary. The method discussed in this paper is applied to speech recognition, speech synthesis, and speech-to-speech translation tasks using speech-text datasets containing audio, transcripts, translated audio, and translated transcripts. The component tasks considered are ASR, AST, S2ST, TTS, and MT, and using datasets with multiple fields resulted in improved performance. Section: Expressing tasks. To specify a task for our model to perform, we introduce a unique task tag before the input data. This task tag also mentions the language in which the input is given and optionally, the output language, if it is different from the input. For instance, if we want the model to transcribe spoken French, we would precede the audio input with a tag such as ASR French. In case we want the model to convert text to speech in English, we'd use the tag TTS English. Likewise, if we aim to convert spoken English to text in French, we would use the tag S2ST English French. These tags are tokenized with the same method that the model uses for normal text. We don't use any special tokens to specify the task or the languages. Interestingly, we found that even if we alter the names of the tasks to be more user-friendly, like using transcribe the following French audio instead of ASR French, it doesn't impact the model's performance. While it's not absolutely necessary to name the language in the task, we could use more generic tags like transcribe audio or AUSR. We found that specifically naming the language improves performance, particularly for languages that have fewer resources available. Section Summary. The model is signaled which task to perform on an input by prefixing the input with a tag specifying the task in the language of the input and output. The tag is tokenized using the normal text tokenizer of the model, and naming the language in the task is beneficial for low-resource languages. Changing task names to be more human-readable does not affect the model's performance. Section: Combined tasks. We're discussing two types of tasks in this context: direct and combined tasks. Direct tasks are those where the model is given an input and it's expected to directly generate an output. In contrast, combined tasks require the model to not only produce the final output but also present the intermediate steps involved in a complex task. This approach is similar to what we call chain of thought prompting. For instance, if we take the task of speech-to-speech translation, S2ST, we might require the model to convert English audio directly into French audio. This instruction is denoted by the task tag, S2ST English-French. But alternatively, we could train the model to work in stages. It first transcribes English audio into English text, then translates the English text into French text, and finally transforms the French text back into French audio. We represent this kind of process with the task tag, AUSR AST S2ST English-French. The beauty of this approach is that the model executes the entire task in one autoregressive decoding pass, rather than making separate calls to the model for each subtask. This allows the model to maintain a continuous focus on the input and all previously decoded content at each stage, providing a more integrated solution as opposed to a pipeline approach where AUSR, automatic speech recognition, MT, machine translation, and TTS, text-to-speech, processes are handled independently. Our observations indicate that this approach of using combined tasks tends to improve the model's performance. We delve deeper into this in the experiment section of this paper. Section Summary. The paper discusses the use of both direct tasks and combined tasks in training models. Combined tasks involve instructing the model to output intermediate steps for a complex task, similar to chain of thought prompting. The authors found that using combined tasks improved performance in their experiments. Section 3.5 Training Mixtures. In this section, we'll discuss the blend of data sources, or mixtures, we use to train our top-performing models. The details about these datasets can be found in another section. We use two main mixtures, each created with the help of the Sakio library. The first mixture was employed for training two models, the AudioPaLM 8B AST and AudioPaLM 2 8B AST. These models generate text outputs and are trained on automatic speech recognition, AUSR, and automatic speech translation, AST, tasks. The second mixture, on the other hand, was utilized to train the AudioPaLM 8B S2ST model. This model produces both text and speech outputs, incorporating text-to-speech synthesis, TTS, and speech-to-speech translation, S2ST, tasks, along with AUSR and AST. Let's delve deeper into what these mixtures comprise of. 1. The AST mixture is made up of several components. AUSR tasks sourced from a range of datasets: CVSS, Vox Populi AUSR, Common Voice 11, Conversational ASIN, and YouTube AUSR. For CVSS and Conversational ASIN, AUSR is applied in both the original and the target languages. AST tasks from the CVSS, Conversational ASIN, and Vox Populi S2ST datasets. For Vox Populi S2ST, we use a workaround method of mapping translated audio to its transcript as the translated transcripts aren't available. A combined task involving both AST and AUSR for the CVSS and Conversational ASIN datasets. Machine translation, MT, tasks sourced from the WMT, TED dataset. 2. The S2ST mixture contains all of the above components and some additional elements. TTS tasks from CVSS and Vox Populi AUSR datasets, where for CVSS we utilize only the original transcript and audio. S2ST tasks from the Vox Populi S2ST, CVSS, WMT, TED, and Palm Mount TTS datasets. However, the speech targets for all these datasets, except Vox Populi S2ST, are synthetically produced. For Vox Populi S2ST, we execute translation both from original to target, and vice versa. A combined task of AUSR, AST, and S2ST using data from the Conversational ASIN, CVSS, and WMT, TED datasets. Generally, we give weights to the components of the mixture according to their volume, while larger datasets are given lesser weight. In a following table, we present the amount of audio data that our models have been trained on with these mixtures. Section Summary. The section describes the data mixtures used to train the AudioPaLM 8B AST, AudioPaLM 2 8B AST, and AudioPaLM 8B S2 ST models. The AST mixture includes ASR and AST tasks from various datasets, while the S2 ST mixture includes TTS and S2 ST tasks in addition to the tasks in the AST mixture. The components of the mixture are weighted based on the number of elements in each component, and table lists the amounts of audio that models trained on the mixtures have seen during training. Section 3.6 Training Setup. We follow the same training setup for all our experiments as detailed in Section 6.1.2 of the reference paper. Specifically, we use the Addifactor optimizer and set the learning rate to be a constant value, which is 5 times 10 to the power of -5. We apply a dropout rate of 0.1 and mask the losses on our input data. We employ several datasets for training AudioPaLM, detailed as follows. 1. CoVost2. This is a speech-to-text dataset which converts speech from 21 languages into English text. 2. CVSS. It augments CoVost2 and generates speech for target text in two ways. CVSSC uses a standard speaker's voice, while CVSST transfers voice characteristics from the source voice. Unless otherwise mentioned, we use CVSSC for our speech-to-speech translation experiments. 3. Vox Populi. This dataset includes speeches from the European Parliament along with their transcripts. It can be used for both speech recognition and speech translation tasks. 4. Common Voice. This consists of text paired with recordings where individuals were instructed to read the text out loud. 5. A conversational dataset. This was obtained by asking crowdsourced participants to read a subset of Spanish text from a Spanish-English machine translation dataset. 6. YouTube ASR. This is an unlabeled multilingual dataset made up of YouTube audio, which was automatically transcribed using the USM2B ASR model. It aids in enhancing models for YouTube to improve captioning and translation. 7. WMT, TED TTS. This dataset is based on WMT and TED text-to-text translation datasets, and it is enriched by converting all source and target text into synthetic paired audio via text-to-speech, TTS, engine. 8. Palm Mount TTS. We use this to provide additional training data for speech-to-speech translation. It involves using Palm 2 to translate YouTube, Common Voice, and Babel transcripts to English, and then using an existing AudioPaLM model to generate the speech. This method is similar to one previously reported that combines machine translation and TTS to generate more paired data. We train our models on a blend of these datasets for ASR, AST, and speech-to-speech translation tasks. In a later section, we investigate how adding more data can improve the performance of our method. It's important to note that our models also benefit from PaLM's text training data and the data used to train the audio tokenizers, thanks to the pre-trained PaLM checkpoints and audio tokenizers we utilize. Although our models are trained on the datasets mentioned, they can still gain from this additional data. Section Summary. The authors use the same fine-tuning setup for all experiments, which includes Addifactor optimizer, a constant learning rate of 5x10 to the power of -5, and dropout rate of 0.1, with loss masking on the inputs. They use various datasets for AudioPaLM training, including CoVost2, Vox Populi, Common Voice, and YouTube ASR, among others. They also use Palm Mount TTS to translate transcripts and synthesize speech, and explore how adding more data improves their method's performance. Section 4.2 Evaluation Metrics. 4.2 Evaluation Methods. We examine the effectiveness of our approach using these benchmarks. CoVost2 AST. Our performance here is gauged by the BLEU scores, which are calculated through the Sacra BLEU Corpus BLEU method. We don't make any modifications or normalizations to the text before calculating these scores. FLIR AST. This dataset includes speech utterances and corresponding transcripts across 102 languages and is used solely for evaluation purposes. Similar to CoVost2 AST, we use BLEU scores as a measure of performance. Vox Populi ASR. For this benchmark, we rely on the GWER implementation of the word error rate, WER. To compute WER, we adjust the text to exclude differences in capitalization and punctuation. CoVost2 ASR. This is similar to Vox Populi ASR, however, for Japanese and Chinese, we provide the character error rate, CER, instead of WER. This metric is specifically reported for experiments conducted on the CoVost2 dataset. CVSSS2 ST. Building on the methodology of Translatron 2, we input the audio output of our model into an automatic speech recognition (ASR) model and use blue scores to compare the ASR output with the original target text. We use the same ASR model for consistency, ensuring the metrics are directly comparable. For all these benchmarks, we conduct our evaluations on the test splits of the respective datasets. Section Summary. The paper evaluates their method on various benchmarks including CO-VOST2-AST, FLIR-AST, Vox Populi ASR, CO-VOST2-ASR, and CVSS South 2 Street. They use blue scores for CO-VOST2-AST and FLIR-AST, word error rate, WER, for Vox Populi ASR, and character error rate, CER, for CO-VOST2 ASR. For CVSS2-ST, they use an ASR model and compare the output with the ground truth target text using blue. All evaluations are performed on the test splits of the corresponding datasets. Section 5 Experiments. 5. Experiments. We conducted experiments to evaluate the performance of our approach in automatic speech-to-text translation, AST, direct speech-to-speech translation, S2ST, and automatic speech recognition, ASR. In this section, we present our top-level results, which demonstrate significant improvements compared to previous methods in AST and S2ST, while also achieving competitive performance in ASR. We also provide ablation studies to analyze the impact of individual factors on our results. In Table 1, we present the results of our method and existing baselines on ASR, AST, and S2ST benchmarks. Our models consist of two variants. The first variant, referred to as AST, is trained solely on AST tasks without using S2ST and text-to-speech, TTS, data, while the second variant, referred to as S2ST, is trained using both S2ST and TTS data, allowing it to generate speech output. To generate the audio for the S2ST results, we utilized SoundStorm. For more details on the training mixtures, please refer to Section 4. As a starting point, we used a PALM-28B checkpoint and extended it to handle audio tokens as input and output, as described in Section 3. The additional audio token embeddings were initialized to 0. Similar to the original PALM and PALM-2 models, the input and output embeddings are shared. Our method outperforms the baselines in AST and S2ST tasks, while also achieving competitive results in ASR. Furthermore, our approach shows comparable performance to a cascaded approach in AST, where we first utilize our best AudioPALM2 ASR model, followed by translation using another AudioPALM2 model that is fine-tuned exclusively for text-to-text translation on CO-VOST2 dataset. Section Summary. The paper presents significant improvements in automatic speech-to-text translation, AST, and direct speech-to-speech translation, S2ST, as well as competitive results on automatic speech recognition, ASR. The models come in two variants, AST and S2ST, with the latter being able to produce speech. The method exceeds baselines on AST and S2ST and is competitive on ASR, and comes close in AST performance to a cascaded approach. Section Setup. You are an archive paper audio paraphraser. Your primary goal is to rephrase the original paper content while preserving its overall meaning and structure, but simplifying along the way, and make it easier to understand. In the event that you encounter a mathematical expression, it is essential that you verbalize it in straightforward non-latex terms, while remaining accurate, and in order to ensure that the reader can grasp the equation's meaning solely through your verbalization. Do not output any long latex expressions, summarize them in words. The text must be written in the first-person plural point of view. Do not use long latex expressions, paraphrase them or summarize in words. Be as faithful to the given text as possible. Below is the section of the paper requiring paraphrasing and simplification, and it is indicated by double-angle bracket setup. Setup. We evaluate the zero-shot capabilities of our AST models on the FLIR multilingual dataset. The dataset contains speech utterances and their corresponding transcripts in 102 languages. Note that none of our models were trained on FLIR, so we use the dataset for evaluation only. In this context, we focus on the language pairs X-English and extract two subsets of languages, 29 AST observed languages, languages for which speech-to-text translation, AST, data, X-N, was seen during training, as these language pairs were present in the Vox Populi S2ST, CO-VOST2 and conversational ASIN datasets. These languages are indicated with a section in Table 26 ASR observed languages, languages for which no speech-to-text translation data was seen when training our AST models, but for which at least 1 hour of transcription, ASR, data was present. We removed 3 languages, Cantonese, Kurdish and Ganda, for which we did not have a blue score for the baseline. These languages are indicated with a in table. Section summary. The authors evaluate the zero-shot capabilities of their AST models on the FLIR multilingual dataset, which contains speech utterances and their corresponding transcripts in 102 languages. They focus on two subsets of languages, 29 AST observed languages and 26 ASR observed languages, for which speech-to-text translation data was seen during training and at least 1 hour of transcription data was present, respectively. None of the models were trained on FLIR, so the dataset is used for evaluation only. Section. Results. In our paper, we present the results of our two proposed models, AudioPaLM and AudioPaLM2, along with a baseline model called Whisper Large V2 1.5b. We also provide information about the number of speech training hours for each of these models in the context of automatic speech translation, AST, and automatic speech recognition, ASR. It's important to note that the reported training hours for the proposed models do not include the time taken to train the tokenizers used in the models. When comparing the performance of the models, we found that the AudioPaLM2 model performs significantly better than the Whisper model for AST observed languages. While Whisper is used as a reference model for ASR observed languages, it's worth mentioning that Whisper's results are not zero-shot because it has been trained on 40.6K hours of speech-to-text translation data for these languages. On the other hand, the AudioPaLM models are zero-shot for these languages since they have not been exposed to any AST data. Despite this disadvantage, the AudioPaLM2 model still outperforms the Whisper model for ASR observed languages. We provide a detailed performance comparison for each language in the appendix. The results show a significant improvement when using the AudioPaLM2 model instead of the AudioPaLM model. There is a 28% increase in performance for AST observed languages and a remarkable 107% increase for ASR observed languages. These numbers demonstrate that the superior text translation capabilities of AudioPaLM2 directly transfer to the audio domain, even though the model has not been trained on any speech-to-text data for these specific language pairs in the case of ASR observed languages. Section summary. The proposed AudioPaLM2 model outperforms the Whisper model on AST observed and ASR observed languages, despite not having seen any speech-to-text data for the latter during training. The AudioPaLM2 model shows a significant improvement over the AudioPaLM model, with a 28% increase for AST observed languages and a 107% increase for ASR observed languages. Section 5.3 Quality of Generated Speech. You are an archive paper audio paraphraser. Your primary goal is to rephrase the original paper content while preserving its overall meaning and structure, but simplifying along the way, and make it easier to understand. In the event that you encounter a mathematical expression, it is essential that you verbalize it in straightforward non-latex terms, while remaining accurate, and in order to ensure that the reader can grasp the equation's meaning solely through your verbalization. Do not output any long latex expressions, summarize them in words. The text must be written in the first-person plural point of view. Do not use long latex expressions, paraphrase them or summarize in words. Be as faithful to the given text as possible. Below is the section of the paper, requiring paraphrasing and simplification, and it is indicated by double angle brackets. 5.3 Quality of generated speech. In addition to measuring the translation quality of the speech content as reported in table, we are also interested in evaluating whether the speech generated by AudioPaLM is A. of high quality, and B. truthfully preserves the voice of the speaker when translating to a different language. To this end, we use a combination of objective metrics and subjective evaluation studies that use the test split of the CVSST dataset. The subjective experiments were conducted on an earlier version of AudioPaLM using the acoustic generation method described in AudioLM. Baselines. As a first baseline, we use the ground truth translated utterances which are provided as a part of the CVSST dataset. These utterances were obtained by synthesizing the ground truth translated text with a high-quality TTS system which was modified to enable voice transfer. As a result, the ground truth utterances mimic the voice in the source utterance. As a second baseline, we use Translatotron 2. Note that we could not use the Translatotron 2 plus pre-training plus TTS August model, mentioned in table, in the comparison because it was not trained to preserve voices and instead generates speech in a single canonical voice. Instead, we use the Translatotron 2 system presented by which is capable of transferring the voice from the source utterance, albeit it achieves a lower blue score on CVSS. This version of the Translatotron 2 model was trained on the CVSST dataset and implements S2ST from 21 languages to English. Section summary. The quality of speech generated by AudioPaLM was evaluated using objective metrics and subjective evaluation studies on the test split of the CVSST dataset. Two baselines were used for comparison: ground truth translated utterances synthesized with a high-quality TTS system modified for voice transfer, and Translatotron 2, which is capable of transferring the voice from the source utterance but achieves a lower blue score on CVSS. Section: Objective Metrics. Objective metrics play a crucial role in evaluating the performance of our system. First, we employ a no-reference mean opinion score (MOS) estimator to gauge the perceived audio quality of an audio sample. This metric assigns a rating from 1 to 5, indicating the quality level. To assess cross-lingual voice transfer quality, we utilize a pre-existing speaker verification model used by previous studies. We calculate the cosine similarity between the embeddings of the source audio, encoded, decoded with soundstream, and the translated speech. Additionally, we measure how well the acoustic properties, such as recording conditions and background noise, are transferred from the source audio to the target. For this assessment, we compute the cosine similarity between embeddings extracted from a model trained to identify segments from the same recording. In addition to objective metrics, we conduct subjective evaluations through two separate studies. The first study aims to evaluate the quality of the generated speech, while the second focuses on assessing voice similarity. Both studies employ the same set of audio samples. However, we notice that some samples contain unwanted elements like overlapping speech, e.g., TV show or background music, or strong noise, e.g., microphone rubbing against clothes. To simplify the task for raters, we pre-filtered the inputs by selecting only those with an estimated MOS of at least 3.0. Ultimately, we obtained 210 source utterances to translate, with 10 examples per language. To ensure consistency and provide guidance to the raters, we took several steps. The utterances were normalized and resampled to 16 kHz if necessary. Raters were given a set of illustrative examples with known ratings as reference. They also underwent a pilot study for training purposes. The raters evaluated the utterances one by one, assigning ratings on a 5-grade scale ranging from 1, poor quality or different voices, to 5, excellent quality, identical voices. In the voice similarity study, raters were explicitly instructed to disregard differences in recording conditions and language and solely focus on the voice. Each of the 630 output examples, 10 inputs from each of the 21 languages, generated using the 3 different systems, was rated 10 times, resulting in a total of 6,300 ratings per study. By aggregating these ratings for each system, we obtained the mean opinion score, MOS, and similarity mean opinion score, SMOS. Section summary. The paper uses objective metrics to measure the perceived audio quality, cross-lingual voice transfer quality, and acoustic properties transfer. For subjective evaluation, 2 studies were conducted to assess the quality of the generated speech and voice similarity. The raters were provided with a set of illustrative examples and completed a pilot study before rating the utterances on a 5-grade scale. The ratings were aggregated to obtain mean opinion score, MOS, and similarity mean opinion score, SMOS. Section: Results. Results. We present the outcomes of our evaluations, both objective and subjective, in table. From these outcomes, we notice that AudioPaLM performs significantly better than the baseline Translatotron 2 system in terms of audio quality and voice similarity, as measured objectively and subjectively. Additionally, AudioPaLM exhibits higher quality and better voice similarity compared to the ground truth synthesized recordings in CVSST, with a noticeable difference in most metrics. Furthermore, we examined the systems across high and low resource language groups, French, German, Spanish, and Catalan versus the remaining languages, and found no significant variation in the metrics between these groups. 5.4 Impact of model and data choices. In this section, we will explain the experiments that led us to determine our final training approach, starting from initial early testing. These experiments demonstrate the influence of individual factors, which build upon each other until we arrive at the final setup described and analyzed in the previous sections. Section summary. The results of the objective and subjective evaluations show that AudioPaLM outperforms the baseline Translatotron 2 system in terms of audio quality and voice similarity. Additionally, AudioPaLM has higher quality and better voice similarity than the ground truth synthesized recordings in CVSST. The impact of model and data choices were also analyzed through experiments to guide the final training recipe. Section 5.4.1 Training on multiple tasks. In this section, we explore the impact of training on multiple tasks using the same data to enhance the performance of our models. Specifically, we examine the effect of incorporating both automatic speech recognition, ASR, and automatic speech translation, AST, tasks in our training process. By utilizing the CoVost2 dataset, which can be used for both ASR and AST, we aim to improve the performance of our models on AST benchmarks. To conduct our experiments, we trained 2 models on the CoVost2 dataset. The only difference between the 2 models is that one was trained solely on the AST data, while the other was trained on both AST and ASR tasks. We used the PALM-8B checkpoint as our base models and employed the USMV1 tokenizer. Our evaluation was focused on the CoVost2 AST benchmark. The results of our experiments are summarized in the table. We observed that incorporating ASR tasks into the training process led to a 2.5 increase in BLEU score, from 16.0 to 18.5, on the CoVost2 AST benchmark. This improvement indicates that the addition of ASR data positively impacted the model's performance, even though ASR itself was not part of the evaluation task. Our hypothesis is that including ASR tasks during training helps the model establish stronger connections between its understanding of audio input and its previous comprehension of text. To further validate this idea, we conducted additional experiments that included both ASR and AST tasks when using the CoVost2 training data. Section summary. The authors trained 2 models on the CoVost2 dataset, one using only AST data and the other using both AST and ASR tasks. They observed that adding ASR tasks improved performance on the AST benchmark, increasing BLEU by 2.5. The authors hypothesized that this is because ASR tasks help the model better connect its understanding of new audio input to its previous understanding of text. Section 5.4.2 Training from Scratch versus Fine-tuning. In this section, we explore the difference between training a model from scratch and fine-tuning it based on a pre-trained PALM checkpoint. Our aim is to examine the impact of using a pre-trained model compared to starting training from the beginning using the same architecture. To set up our experiments, we initialize the weights randomly for the 1B from scratch and 8B from scratch models. For the 8B fine-tune experiment, we begin with the PALM-8B checkpoint and make modifications by adding extra rows to the token embedding matrix for the audio tokens. These additional rows are randomly initialized. All 3 models are trained on CoVost2 ASR and AST tasks. Now, let's move on to the results. By referring to the table, we can observe that fine-tuning the PALM-8B checkpoint leads to significantly better performance compared to training from scratch on the CoVost2 tasks, both for ASR and AST. We also conducted the 1B from scratch experiment to see if a smaller model architecture would perform better than the 8B model when trained from scratch on CoVost2. However, the results indicate that it does not offer an advantage. Section summary. The section compares the performance of training a model from scratch versus fine-tuning a pre-trained PALM checkpoint on CoVost2 ASR and AST tasks. The results show that fine-tuning the pre-trained model achieves significantly higher performance than training from scratch, regardless of the model size. Section Discussion. Discussion. When we fine-tune a pre-trained checkpoint, we observe significant improvements in the results. This is not surprising considering the strong capabilities of the base model. However, it is interesting to note that with fine-tuning, the model can adapt to entirely new input stimuli. In this case, the audio tokens serve as new embeddings that the model needs to learn and understand. It's important to highlight that audio tokens are quite different from text tokens. Despite the low sampling rate, there is likely some redundancy in the audio data, and the rate of samples is much higher compared to text tokens. Based on our analysis, we estimate that at a sampling rate of 25 Hz, one text token corresponds to approximately 6 to 8 audio tokens. Different tokenization schemes. To obtain the results presented in the previous section, we applied the USMV2 tokenization scheme to the audio. In this section, we explore the impact of different tokenization schemes on the final outcomes. We conducted experiments using 3 models, with all conditions held constant except for the tokenization scheme applied to the audio. These models were trained using the PALM-8B checkpoint. In each case, we used the CVSS datasets with ASR and AST tasks, and the source audio was preprocessed using different tokenizers. The 3 tokenizers used were the W2V BERT, USMV1, and USMV2 tokenizers, which were discussed in the previous section. Section summary. The study found that fine-tuning a pre-trained checkpoint significantly improves results, allowing the model to adapt to new input stimulus. The choice of tokenization scheme also impacts the final results, with 3 different tokenizers used in the study: W2V BERT, USMV1, and USMV2. All models were trained using the PALM-8B checkpoint and tested on the CVSS datasets with ASR and AST tasks. Section: Results. Results. Our findings indicate that the choice of tokenization scheme significantly influences the model's performance. Specifically, we observed that the USM encoder outperforms the W2V BERT encoder, leading to improved performance in our experimental setup. Moreover, the USM-V2 tokens demonstrate even better performance, resulting in substantial enhancements. Discussion. It is not surprising that the tokenization scheme has a considerable impact on the model's performance. The tokenizer captures the information that the model is exposed to, and this information can be presented in a way that is either easy or challenging for the model to process. Therefore, future research should pay careful attention to audio tokenization as it is still an evolving field of study. Training with combined tasks. To achieve the results presented in section number, our approach involved the model performing intermediate steps for complex tasks by combining multiple tasks into a single process, as explained in section number. In the following analysis, we examine the influence of this approach on the overall performance. Section summary. The choice of tokenization scheme greatly affects the performance of the model, with USM-V2 tokens yielding the best results. The authors suggest that future work should focus on improving audio tokenization, as it is still a relatively immature research area. The model's ability to compute intermediate steps for complex tasks by combining multiple tasks into one also had a positive impact on performance. Section: Setup. In our study, we conducted experiments using the CoVost2 AST dataset to train pairs of models. Each pair consisted of two models, with the only difference being the training tasks. One model was trained with automatic speech recognition, ASR, and automatic speech translation, AST, tasks, while the other model included an additional combined task. In the combined task, the model first performed ASR and then generated the AST output based on the ASR result. During evaluation, we reported the results of the combined task, considering only the final output. We repeated this setup twice, using two different token sets, USMV1 tokens and USMV2 tokens. The results are presented in the table. The table demonstrates that when we express the AST task as a combination of simpler tasks, the performance on the AST task improves. However, there is a slight decrease in performance on the ASR task. These results align with previous studies that have observed the benefits of allowing models to break down complex tasks into simpler components, leading to improved performance compared to directly outputting the answer. The decrease in ASR performance may be attributed to our selection criterion for checkpoints, where we chose the checkpoint with the best AST metric on the validation set. Additionally, the change in data mixture resulting from this modification could also contribute to the decrease. It may seem that the combined tasks reduce the problem to a pipeline approach with separate ASR and translation systems. However, this is not the case as our model is a single unified model that can refer to all previous tokens at each step. For example, during the decoding of translated text, the model can access the input audio and any information contained in it. This is particularly important in the S2ST setting, as described in the experiment section, where prosodic information may be present in the input audio and can be considered while generating the output audio. Section summary. The authors trained pairs of models on the CoVost2 AST dataset, with one model trained on ASR and AST tasks, and the other trained on a combined task of ASR followed by AST. Results showed that expressing the AST task as a combination of simpler tasks improved performance on the AST task, but resulted in a small reduction in performance on the ASR task. The authors hypothesized that this reduction may be due to their checkpoint selection criterion or the large change in data mixture resulting from the change. Section 5.4.5 Training with additional speech-to-speech tasks. In this section, 5.4.5, we explore the effects of incorporating speech-to-speech translation, S2ST, tasks into our training process. We conduct experiments using the CoVost2 dataset and train two models accordingly. The first model is trained solely on the tasks of automatic speech recognition, ASR, automatic speech translation, AST, and the combined AST task. This model only generates text tokens as output. The second model, in addition to the aforementioned tasks, is trained on S2ST tasks both independently and in combination with the other tasks. This means that the second model is exposed to tasks where it needs to produce audio tokens as output. Unlike the previous tasks, which involved generating text tokens, the S2ST task requires the model to output audio tokens. The results are presented in the table. We observe that incorporating the S2ST task enables the model to perform speech-to-speech translation. However, this improvement in capability comes at a modest cost. Both the AST Blue score and the ASR WER score show a slight decrease when evaluating on the CoVost2 test split. Upon further examination, we find that the process of performing S2ST differs fundamentally from ASR and AST. The model receives audio tokens as input for ASR and AST, but due to the use of loss masking, it doesn't need to explicitly learn to model sequences of audio tokens. However, with S2ST, the model must learn to generate audio tokens, which requires additional capacity. This explains the decrease in performance on the text output tasks since some of the model's capacity is now dedicated to audio modeling. Section Summary. The impact of adding speech-to-speech translation, S2ST, tasks to the trained tasks was investigated using the CoVost2 dataset. The addition of S2ST resulted in the new capability of performing S2ST, but at the cost of a modest decrease in performance to both the AST BLUE score and ASR WER score when evaluating on the CoVost2 test split. The model must learn to emit audio tokens for S2ST, which is fundamentally different from ASR or AST, resulting in a decrease in performance on the text output tasks. Section 5.4.6 Scaling the training data. In this section, we examine the impact of increasing the amount of training data on our models. We conduct our analysis using two types of models, AudioPaLM 8B and AudioPaLM 8B-S2ST, both trained from a PaLM 8B checkpoint and with USMV2 tokens. The AudioPaLM 8B models are trained without the S2ST tasks, while the AudioPaLM 8B-S2ST models are trained with the S2ST tasks. We train these models with progressively larger amounts of data. The training data scenarios we consider are as follows. 1. CoVost2 dataset only. For the S2ST model, we use a modified S2ST version of this dataset called CVSS. 2. All the public datasets described in table, including CoVost2, CVSS, Vox Populi AST, Vox Populi S2ST, Common Voice 11, and Conversational ASIN. 3. All the public datasets mentioned above, along with the YouTube ASR dataset. 4. All the public datasets mentioned above, along with the YouTube ASR dataset and the WMT, TED text-to-text translation dataset. 5. For the S2ST models, we create a paired S2ST dataset by following the same approach and synthesizing the examples in this dataset using TTS. 6. Similar to the previous scenario, but instead of the YouTube ASR dataset, we use the synthetic PaLM-based Mount TTS dataset called S2ST mixture. To create this dataset, we translated the transcripts of the YouTube, Common Voice, and Babel datasets to English text using PaLM-2 and then synthesized the English speech. By exploring these different data scaling scenarios, we aim to understand the effects of increasing the training data on our model's performance. Section Summary. The impact of increasing the amount of training data on two types of models, AudioPaLM 8B AST and AudioPaLM 8B-S2ST, both trained from a PaLM 8B checkpoint and with USMV2 tokens, was investigated. The models were trained with an increasing amount of data, ranging from the CoVost2 dataset only to all public datasets, as well as the YouTube ASR dataset and the WMT, TED text-to-text translation dataset. For the S2ST models, a paired S2ST dataset was synthesized using TTS on the examples in the dataset. Section Results. Results. Our findings, as presented in table, demonstrate a significant improvement when training with larger amounts of data. Specifically, in line with experiment, we find that incorporating additional ASR data enhances performance in AST tasks. Furthermore, consistent with experiment, we notice that when comparing fixed dataset mixtures of AST and S2ST, including the S2ST tasks introduces new S2ST capabilities at the expense of a slight decrease in AST performance. All S2ST results in table utilize AudioPaLM Stage 2 and 3 models to reconstruct audio samples from audio tokens, as explained in section. Discussion. It is not surprising that increasing the training data quantity leads to improved performance. We observe that, in some cases, augmenting the data results in a minor decline in ASR task performance, while consistently enhancing the performance in AST tasks. This behavior may be attributed to our selection criterion for checkpoints, which is based on AST performance on the CVSS validation set, similar to experiment. Section Summary. The study shows that increasing the amount of training data leads to a significant improvement in performance, particularly when additional ASR data is added to AST tasks. However, adding S2ST tasks to the dataset mixture results in a slight decrease in AST performance but brings new S2ST capabilities. The authors note that this is expected and may be due to their checkpoint selection criterion. Section 5.4.7 Decoding with AudioPaLM versus SoundStorm. In this section, we examine the effects of decoding using AudioPaLM Stage 2 and 3 models versus SoundStorm on the S2ST metrics. To conduct our experiment, we utilize the best AudioPaLM model from the previous section, which was trained using a combination of public, palm-mount TTS, and WMT, TED datasets. The previous experiment involved decoding the audio tokens generated by AudioPaLM into wave audio using AudioPaLM Stage 2 and 3 models. For comparison, we rerun the experiment using a SoundStorm model instead and measure its impact on the CVSS2ST task. The results are presented in the table. We observe a 1.3 blue point increase when using SoundStorm compared to AudioPaLM. This outcome corresponds to the S2ST model presented in the table, which was trained on the S2ST mixture described earlier. The discussion of these results aligns with findings reported in previous studies, which indicated that SoundStorm produces speech that is more intelligible compared to AudioPaLM when used for decoding semantic audio tokens. Intelligibility was assessed by measuring the similarity between the resulting audio and a ground truth transcript when transcribed with an OSR system, similar to our experimental setup. Section Summary. In this section, the impact of decoding using AudioPaLM Stage 2 and 3 models versus SoundStorm on S2ST metrics was investigated. The best AudioPaLM model was used, and a 1.3 blue point increase was observed when using SoundStorm compared to AudioPaLM. These observations are consistent with previous findings that SoundStorm produces more intelligible speech when used to decode semantic audio tokens. Section 5.4.8 Impact of using PaLM2. In this section, we investigate the impact of using the PaLM2 checkpoint compared to the original PaLM model. PaLM2 was trained with better data and techniques and specifically included parallel translation data. Our goal is to determine whether these improvements result in better performance in speech tasks. We focus on speech-to-text (STT) tasks and exclude speech-to-speech translation (S2ST). We train two sets of models using the largest datasets discussed in the previous section. For each dataset, we train two models, one utilizing the PaLM8B checkpoint and the other utilizing the PaLM28B checkpoint. Unlike the PaLM fine-tuning experiments, we used different optimization hyperparameters. Specifically, we employed a dropout rate of 0.2 and a learning rate schedule that begins with a linear ramp up to 10 to the power of -4 and then decays exponentially to 10 to the power of -5. Examining the results presented in the table, on the smaller dataset mixture, we observe an improvement in the CoVost2 AST task with PaLM2. However, there is a slight decrease in performance for Vox Populi OSR and a more significant decrease for CoVost2 OSR. On the larger dataset mixture, PaLM2 outperforms PaLM in Vox Populi OSR and CVSS AST tasks, but it performs slightly worse in CoVost2 OSR. Our interpretation of these findings is that the enhanced text translation capabilities of PaLM2 contribute to improved performance in AST. However, the impact on OSR capabilities is mixed. When using the complete training mixture, PaLM2 exhibits slightly worse OSR performance on CoVost2 but slightly better performance on Vox Populi OSR. Section Summary. The section explores the impact of using the PaLM2 checkpoint compared to the original PaLM model in speech-to-text tasks. PaLM2 was trained with improved data and techniques, including parallel translation data. Results show that PaLM2 exceeds PaLM on some tasks, such as Vox Populi OSR and CVSS AST, but is slightly worse on CoVost2 OSR. The improved ability of PaLM2 to perform text translation leads to an improvement for AST, while the impact on OSR capabilities is mixed. Section Discussion. Discussion. We observe a difference between PaLM and PaLM2, but we believe that the variations in capabilities between the two models are not as crucial in this context as they would be for tasks that solely involve text. This is because the inclusion of tokenized audio is a new aspect for both models. Impact of architecture scale. Next, we explore how the size of the model affects its performance on downstream tasks. To investigate this, we utilize PaLM2 and focus on the OSR, automatic speech recognition, and AST, audio-to-text, settings. Setup. We train three PaLM2 models with different sizes, 128M, 1B, and 8B, using USMV2 tokens. These models are trained on the same two largest datasets mentioned in the previous section. We then evaluate their performance on our benchmark OSR and AST tasks. Results. The results, as shown in the table, indicate that increasing the model size significantly improves performance. Specifically, when transitioning from a 128M to a 1B model, we observe a 42% reduction in word error rate, WER, for the CVSS, Common Voice Sentence Corpus, and Vox Populi OSR tasks. Additionally, we observe an increase of over 13 points in blue scores for translation tasks on the full public plus YT plus WMT, TED dataset. Further increasing the model size from 1B to 8B leads to additional improvements. We observe an additional 10% and 16% reduction in WER for the CVSS and Vox Populi OSR tasks, respectively. Furthermore, there is a 6.2-point improvement in blue score. These scaling improvements hold true across different training datasets, such as public plus YT compared with public plus YT plus WMT, TED. Section Summary. The impact of model size on downstream task performance was investigated using 3 PaLM-2 models of different sizes, 128M, 1B, and 8B, on OSR and AST tasks. Results showed that increasing the model size led to substantial improvements in performance, with up to a 42% reduction in WER for CVSS and Vox Populi OSR tasks and over a 13-point increase in blue scores for translation tasks. The scaling improvements also held across different training datasets. Section. Discussion. As we anticipated, increasing the size of the model leads to better results in tasks related to automatic speech recognition, OSR, and automatic speech translation, AST. Our model, which is 1 billion, 1B, in size, performs significantly better than the Whisper 1.5 billion, 1.5B, large model. Specifically, our model achieves an improvement of over 5 blue points and a 28% reduction in word error rate, WER, in the Vox Populi OSR task. Section Summary. The section discusses the impact of model size on the performance of OSR, AST tasks. The larger the model size, the better the performance. The 1B-sized model outperforms the Whisper 1.5B large model by 5 blue points and reduces WER for Vox Populi OSR by 28%.